Okay, good evening, everyone. This is my second video. As I said, I will do three separate ones for each section. So the second one is focused on 8.3, the last system of coordinates, the complex coordinate system. Now we refer to the complex coordinate system as the largest system that is a union of the rectangular coordinate system and the polar coordinate system. So together they create the complex coordinate system. So that means for the complex system will be one design of the complex numbers that are in the rectangular form, and then one design of complex numbers that are in the polar form. Before I start, when we operate, numbers must be in the polar complex form before you apply operations. So operations that we are going to see are three. First group of operations, multiplication. Second group, division. So you're going to find the quotient, you're going to find the product. And the third group is raising a polar number into a power n, where n is a positive whole number. Now, what is the way we introduce the polar coordinate system? This introduction will be based on the two different ways of writing complex numbers. So complex polar numbers and complex rectangular numbers. A complex number is defined by a letter Z, and it will be a rectangular standard form of a complex number that I believe you've seen it in your pre-calculus courses and you already operated with. That's not what we are focusing on. And then the second one is the polar complex standard form, and that's the one that is going to be at the center of the three operations that we are discussing. So I'm going to start off by sharing. First thing I'm going to share is a PowerPoint of the polar system. So let's go ahead and share. And then I'm going to go to the slideshow view. So complex numbers in the polar form. So we start with the normal introduction, which is the rectangular standard form of the complex number. Complex numbers are defined by the letter Z. And then a rectangular form is the one that you've seen when you studied for the first time the complex system. A number Z is in the form of 8 plus BI. Notice the presence of the letter I. I stands for the imaginary numbers. A is called the real part of the complex number, and B is called the imaginary part of the complex number. When we do the graphical presentation, remember when I introduced the polar coordinate system today, I transitioned every single element of the rectangular coordinate system into the polar system. We do exactly the same thing for the complex system. Now the transition is going to include the transition of the horizontal line, x-axis, into the real line, which is horizontal. We refer to the line as the real line. So the old horizontal line x-axis, it's going to continue to be a line, but becomes the real line. So this is where you find not x coordinates by the a coordinates. So remember what a is. A is the real part of the complex number. Now the second axis is the vertical line. The old y-axis is going to continue to stay as vertical, but becomes the imaginary axis. And this is where we are going to get the coordinate b. So the y becomes a b, x becomes an a. Because I want you to see that transition, because I'm about to transition the formulas. Whatever is an x will be replaced by an a, and then any y will be replaced by a b. So that's the easiest way of understanding this transition. So as I said, the real axis is the old horizontal axis. That's the real part of the complex number. And the imaginary axis is the vertical line. So the y-axis becomes the imaginary axis, representing the imaginary part of the complex number. Together, they create what is known as the complex coordinate system, the complex plane. And this is the number Z that I was referring to. So this given is A plus BI. As I said, this is not a new form. So this is not the first time. I'm hoping you remember this. It's an entire large section in Algebra 2 at the end of Algebra 1 in Pre-Calculus 1, Chapter 3, operations with complex numbers. And that's what you've seen. Number Z stands for the complex numbers, and then their standard form, it's A plus BI. What you're learning new, this standard form that you used in the past and you operated, now precisely is known as the complex rectangular form. Why? Because of that transition of X and Y. So X is A and Y is B. The order pair XY now becomes AB. So at the center of the complex coordinate system stands the order pair AB. When you plot points, you are going to plot them the same way you plot a point with the coordinates X and Y. Now, how do you know that you're plotting in a complex system? Because the way we name the axis, we call horizontal line a real axis and the vertical line the imaginary axis. This is how you understand, okay, now I'm plotting a point using A and B in the complex plane or the complex coordinate system. And now let's look at a point that is already plotted in the complex system. Notice that the horizontal line is the real axis, the vertical line is the imaginary axis. Point represented by the red dot is the point 2 plus 3i, so that's the complex number Z, where the value of A is 2 and the value of B is 3. So the order pair representing this point is 2, 3. And then in the third quadrant, the dot sign represented with the blue color, complex number is -1 minus 2i, where A is a -1 and B is a -2. So when you read the number in front of I, you're not only reading the numerical value, but the sign in front of it. So the order pair corresponding to the dot blue sign or the blue dot point is -1, -2. A is -1, B is -2. So now let's see how the formulas are going to change. But before we do that, let's do an extra example of plotting points. And then I'm going to get into the transition of the formulas, and then I'll start typing in, going back to my document. So plotting -1, -5i. The first number represents A. That's what you get on the real axis, on the horizontal line. And the second number represents B, -5. That's what you need on the imaginary axis, which is the vertical line. So we are going 1 unit to the left horizontally, 5 units down. So let's see if that's the case. Yep. Now, how do I understand and read this point that is just the 3i? So you only see 3, which is B, in front of the letter I. That's the imaginary part. What you don't see, what you're missing, is the real part. And anytime you're missing one of them, you're represented by a 0. So I write this as a 0 plus 3i, which makes A equals to 0 and B equals to 3. The real part is fully missing, so that's automatically 0. So 0, there are no movements horizontally. You stay at the center, but you're moving 3 units up on the imaginary axis. And that's the point, 0 plus 3i. In the last one, I notice the presence of the real part, which is -4. That's going to be A, but I don't see the imaginary part, so automatically B is 0. So another way of writing this point is -4, 0, which means you're going 4 units to the left on the real axis, and there are no movements horizontally on the imaginary axis. Let's write out order pair -4, 0, and that's the point. This is how you write the complex number -4 plus 0i. So notice that if you're missing the imaginary part, B, which represents the imaginary part, will be substituted by 0. And let's see the transition of the formulas. That's a good practice for all of you. So for the transition of the formulas, I'm gonna stop sharing the PowerPoint and then go back to my notes. And then share the same file that I was working on. So section 3, complex coordinate system. We refer to this one as CCS. So there are 3 systems. The complex coordinate, it's more like merging the rectangular coordinate system known as RCS and the polar coordinate system known as the PCS. Now for each one of them, we do have a form representing each system, and then we just started with the one related to complex rectangular form. The complex rectangular form is Z equals A plus BI. And then order pair is A comma B. So that allows us to clearly see the transition of X and Y into A and B. Now the question is how the formulas that we already introduced are going to change. So let's go back and then pull out the formulas that we actually used in the previous examples. So 2 of the formulas are so let's go back. Two of the formulas are X equals R cosine of theta. So remember, X is your A, and then Y is B. That's my first transition. Now, what is my second transition? Remember, we had tangent theta, and then we had R squared. So now I'm going to work to transition these 2 other formulas into the complex form. So how the other 2 are going to transition? Of course, I'm not going to change tangent theta, but Y becomes a B, and then X becomes an A. Now this R square no longer stands as an R square. R square will be replaced by Z, and therefore Z is nothing but A squared plus B squared. When you take the square root of this A squared plus B squared to get Z by itself, then you create an important formula that is known as complex modulus. So we call, to make sure that this is going to be positive, we call it absolute value of Z. That's going to secure a Z being positive all the time. And this is the square root of A squared plus B squared. So the modulus is the absolute value of Z. It's not very popular because that kind of like transforms the design of the order pair R theta. So I'm going to continue to keep this as R because that's what you are going to see for the modulus. So as we transition, Let's call this R. And then now we officially have a name for R. So R represents the modulus of the complex system. Now, if you're wondering what is theta, theta, by the way, is known as the argument. If you're taking science or physics specifically as a class, these are going to be the two popular terms, because in physics, in many applications, you have to rely on this particular system, especially the polar one. And then using the term modulus and argument is very common in different applications. So this brings us into, we just introduced the complex rectangular form. Then what is the complex polar form? So from the complex rectangular form to the complex polar form. The complex polar form is defined by Z being equal to R times cosine of theta plus I sine of theta. So any complex number in this particular form is known as a complex polar number. And then, of course, the order pair is indeed the R and theta order pair. So we do have, instead of X and Y, we have an AB order pair that gives us the complex rectangular form. And then we have, of course, R and theta. These two coordinates are staying the same, even though you create the complex polar form. Now, this complex polar form is extremely popular, and it is the only form that we use to operate in the complex polar system. So using this form, you are going to see how we perform operations such as multiplication to get the product, or operations such as division to get the quotient. And then we'll finalize with a formula that is related as the de Moivre. And then I'll get into the PowerPoint just to allow you to see the name precisely. And then each of the formulas introduced. So the division, the multiplication, the multiplication, the product, and the division. And then, of course, introduce the de Moivres. And then as we do that, we are going to look at one example from the practice quiz 6, and then one very interesting example that is part of my lecture notes. So let's start off with the formulas that are giving us opportunity to perform operations such as multiplication and division. So at this point, I'm gonna stop sharing. Of course, I'm going to save what I've done so far. And then what I'm going to share will be the PowerPoint. I apologize for going back and forth, but from the current slides, there we are. Escape this. That's not what I was looking for. This is my current slide. There you go. So compute the product and the quotient of complex numbers in the polar form. Remember, the number has to be in the polar form. Now, you all understand if I computing the product and the quotient, I have to have two complex numbers. So I'm going to call them Z1 and Z2. Because of that, number 1 and 2 that are used to distinguish the two numbers from one another, you notice that the modulus R takes an index 1 and the argument an index 1 or 2. So how do I multiply these two numbers? I call it Z1 times Z2. When you multiply the modulus of the first with the modulus of the second. And what you do with the arguments, you simply add them up. So theta of the first will be added to theta of the second. And then if you do this for cosine, you don't need to show any work for sine because it's the same number. This can be done if the argument is in the radian measure, which is going to require with some operations with fractions. And then it's very straightforward when it comes to degrees. Now, what's going to happen with the division? If Z1 is divided by Z2, then the modulus of the first order counts is divided by the modulus of the second. Order counts again. The arguments are not added. From the first, you're going to minus the second. So let's try to understand this by looking at one example in the PowerPoint that is already broken down to allow you to understand it. And then I'll stop sharing. I'll go back to my notes and then solve the question that is part of quiz number 6. That is going to be question 5 of practice quiz 6. Here's the example. Your number Z1 is given as 20 cosine of 30 plus I sine of 30. So making sure that the number is in the polar form, complex polar form, which is correct. So I understand that R, the modulus, is 20, and the argument is 30 for the first number. Second number, R is 3, and then theta is 210. My goal is to multiply them together. So when I multiply, the modulus of the first must be multiplied with modulus of the second, and then the arguments are going to be added together. So let's say. So how do I multiply Z1 and Z2? 20 is the modulus of the first, is multiplied by 3, which is the modulus of the second. Cosine and sine are going to stay as they are. I stays as it is. But the angles, which are the arguments, or thetas, are going to be added. So 30 plus 210. So this is 60 cosine of 240 plus I sine of 240. That's all you have to do. And we are going to repeat this process for the question 5 of your practice quiz 6. Now let's look at one with a division. So Z1, this is one with pi, which is interesting. Z1 now has a modulus 8, but the argument theta is 7 pi over 12. Z2 has a modulus 2, but the argument is pi over 4. And then I'm not multiplying, I'm dividing. So when I divide, the modulus of the first order counts must be divided by the second. So that means 8 must be divided by 2. When it comes to the argument, from the first argument, which is 7 pi over 12, you're going to minus the second, which is pi over 4. And this is where you're running into some operations with fractions. As they are, you cannot perform that operation unless denominators are the same. So one denominator is 12, the other one is 4. So you want to make the second one equals to 12 if you multiply the top and the bottom by 3. So you write that as 7 pi over 12 minus 3 pi over 12. 7 pi over 12 minus 3 pi is 4 pi over 12, which reduces to pi over 3. So once again, you multiply pi over 4 by 3, so you get 3 pi over 4, 3 pi over 12. Denominators now are the same. So 7 pi minus 3 pi becomes 4 pi over 12. So 4 pi over 12 are both divisible by 4, so you get rid of 4 and you get pi over 3, because 12 divided by 4 is 3. So now the new argument after you dividing is pi over, after you subtracting is pi over 3. And then the new modulus, due to the division of 8 by 2, is 4. And that's the quotient of Z1 over Z2. Now what I'm going to do is, I will repeat this process as I'm stop sharing. And then I'm going to share the file where my notes are, and then show you practice quiz number 6, and that's going to be question 5. This is what is given. You are performing the operation. I need to get my notes. There you go. So the first number is Z1. So now I have to type in the given as 6, and you can look at the copy that I gave you in class. You should be able to find this question. Copy of the practice quiz 6. Cosine, the argument is 2 pi over 7, by the way. So it's a radian argument, radian measure. That's what I meant. Plus I, and that's going to be sine of 2 pi over 7. It's the same argument. Oh, I accidentally did something wrong when I try to copy this. So checking the argument is 2 pi over 7. Wonderful. So it will be the same argument for the function sine. So this is the first number. Now the second number is z with an index 2. Once again, that index, it's only used to tell you that these are two different numbers. So you cannot use z for both if they are given with different arguments and different modulus. So the z2 is 8, has a modulus 8. And now let's look at the argument. The argument is 3 pi over 8. So to make things a little bit more interesting in terms of finding the least common denominator and then all that stuff. So I'm going to, hopefully not deleting this, I'm going to 8i sine of the same argument, close friend. Now what question 5 is asking me to divide first. That's part A. Then after I divide, multiply. So I'm going to do them in order as it is in your quiz. What did I do? There you go. So how do I divide these two numbers? Let's start with the division first. So that means I'm dividing this little z1, which I can place it in there, by the z2, and let's place it in there. There you go. Now when I divide the modulus of the first, the order counts, even though you have a 6 at the top and 8 at the bottom, that's still okay. You cannot change that order, by the way. Yeah, how? I don't know why the font size. Okay, I'm good. So I got modulus of the first 6 divided by modulus of the second. So now I'm going to get to cosine. What's going to happen with this? I have to use parentheses because it's going to be 2 pi over 7 minus 3 pi over 8. Remember, I'm dividing. So when I divide, this argument must be subtracted. Okay? And now that I already created this set of parentheses, I can copy and paste it. And then I need another set of parentheses. That's it. So this is how you set it up. And when I set up the product, I will more likely copy paste and then make adjustments. So the entire focus now is on simplifying because this is not going to be my final answer. So 6 over 8 has to be simplified. They both are divisible by 2. So I'm going to write this as 3 over 4. Now what's going to happen to the rest of it? I have to focus on this difference between the two complex numbers, between these two radian measures or two fractions. 7 and 8 are denominators that have nothing in common. So in order to find their least common denominator, each fraction must be multiplied by, so 7 must be multiplied by 8 and 8 by 7. Their least common denominator, by the way, is 56, which is the product of 7 and 8. That's what we normally do when the denominators don't share anything. So I'm going to start with 2 pi and then multiply this by 8. And then, of course, 7 times 8 turns into 56. And then another 56. I forgot the difference between them. And then on the other side, I have 3 pi that is multiplied by 7. So now you notice that these two fractions have the same denominator, which allows me to merge them in one. Denominator 56, and I'm going to write down the top. So that's 16 pi minus 21 pi. And that's going to be negative fraction form 5 pi over 56. And then all I have to do now is plugging in, and you don't need to change anything or make any other adjustment. That's going to be your final. So all this entire expression now, which I'm copying and pasting. What did I do? Oh my God, I messed up something. That's not good. I apologize. So let me retype it. As I was trying, more likely rushing to do things. So cosine, and then I had this. Sorry about that. There you go. Plus I sine, and then let's copy this one. Now it's easy for me to copy. I don't know why. I accidentally did it. There you go. Okay, wonderful. There you go. So this entire expression now, I'm going to rewrite it using the outcome of the difference between the arguments. And then, of course, the simplest form. So let me copy and paste and then make the adjustment. We just simplified 6 over 8 into, they both are divisible by 2, into 3 over 4. And then this expression right there must go. Of course, I need the minus. At the top, the 3 becomes a 5, and then the 8 becomes a 56. And that's it. That's the quick adjustments in terms of typing in. So that makes that a 5. And then I'm going to make this a 56, and that's the 5. So that takes care of what is the quotient of these two complex numbers. Now, I'm going to transition into their product. So I will do another copy and paste of this, even though you're thinking, I don't know why you're copying and pasting all these things. And there's a reason why I'm doing it. Now I need to build up my product. So what I'm doing is I'm multiplying Z1 by Z2. And taking advantage of a few things that are already in there so I can copy and paste. So I can no longer use this ratio 6 over 8. Now what's going to happen is argument 6 will be multiplied by the argument 8. The cosine of, the modulus 6 will be multiplied by modulus 8. Now, when it comes to the arguments, they're no longer subtracted, but they're added. See, this was an easy fix. So then again, I have to focus on this thing right there and then work with the least common denominator, which I already did it. So I'm going to, again, copy and paste this thing and then make adjustments accordingly that are going to correspond now to the sum. So the difference, now it's an addition. So that's going to be an addition. And then, of course, there is no longer a minus sign because you're adding. And 16 plus 21, it's going to be a 37. That's my easy fix. And then when I apply the fixed argument into the formula, here's the one that I need to copy again. Now, if you do like a paper base, you don't have to do all this copy and paste thing because I have to do it. 37 and the 8 becomes a 46. Let me get rid of one fraction. So 37 and then the denominator of 56 and you have it. So this is the product and then I can highlight this for you to see it. And let's get to the quotient. Where's my quotient? Right there. But in order for you to do this operation, you must have a complex number in the polar form, okay? So now let's look at, let me save this. That's extremely important. I'm going to stop sharing this one and then I will get to PowerPoint again. But this time, what I'm going to share with you, it's a special formula we refer to as the de Moivre. De Moivre was a French mathematician who did a lot of work on complex polar and coordinate system. We recognize the work that he did. One part of the work is generating the formulas that allow you to compute the powers of complex numbers. De Moivre's theorem is extremely popular. We use actually the result of the theorem that allows you to compute powers of complex numbers. Now, before I share the formula with you, again, reminding everyone the numbers must be in the complex polar form for the formula to work. So what is the de Moivre's theorem or the de Moivre's formula? A complex number z given in the polar form, where r is the modulus and theta is the argument, and the polar form is z equals r cosine of theta plus I sine of theta, and n is the positive integer, can be raised to the power n using the de Moivre's formula. And this is one formula that saves you an amount of time that sometimes, and then operations that sometimes can be can be turned into very complicated, tedious operations with very high opportunities and chances to mess up. So what de Moivre did, if you have a complex number in the polar form and you're raising, let's say, to the power 10, you don't need to multiply the number by itself 10 times. This is how the shortcut works with the de Moivre's theorem. All you have to do is take the modulus, raise it to the power n. So the modulus r is raised to the power n. And then each argument theta must be multiplied by n. That's all you do. And the rest of the number does not change. So once again, if n is a positive integer, which means positive integers are numbers such as 1, 2, 3, 4, 5, and so forth, countable numbers. So if n represents the exponent and z is a complex number in the polar form, I cannot emphasize this enough. The operations that I'm sharing with you require the complex number to be in the polar form. Then you can compute the power of the complex number by simply raising the modulus to the power n and multiplying the argument by n without changing anything else. So let's practice with one example. So I'm going to escape this, stop sharing, and go back to my example. The example that I'm using, it's going to be an example, again, relying on practice quiz. And this is practice quiz number 6. This is the last question, question 6. And this, by the way, these recordings are going to help you with the review for the upcoming quiz 6. So what are we trying to do? There's a complex number using the de Moivre's theorem. There's a complex number z. Now, in your quiz form, you don't see Z. So I'm going to type it in as it is. So everyone, it's kind of like aware of how the question is given. So I'm typing in, use De Moivre's theorem to find. And this is what I'm finding. As I said, I'm writing this as it is so you can understand exactly how to operate with this. Plus I sine of 15 degrees and then this has to be raised to a power 3. So what is my understanding of this? This entire number that you see in there looks like a Z in the polar form. So all you can do is you can write this as Z to the power 3. Now what the De Moivre's theorem is saying. Here's the De Moivre's theorem. The De Moivre's theorem is saying that if you have Z raised to a power n, where n is a positive integer or a countable number, then the modulus r must be raised to the power n. And when it comes to the argument must be multiplied by n. So n times theta means that argument theta is multiplied by n. And this is true if the number z is given as r cosine of theta plus I sine of theta. You cannot use this formula unless the number is given in the polar form. Complex polar form. This is extremely important. Otherwise, it's not going to work. Okay. So let's try to focus on our number and let's see how that's going to be computed. So notice now that I'm computing z to the power 3. According to De Moivre's, my modulus is 8. So that means I'm going to take 8 and then raise it to the third power. And then theta, which is 15 degrees, will be multiplied by 3. So I'm going to do 3 times 15 degrees. Plus the same thing, I sine of 3 times 15 degrees. It's the same thing. Close parenthesis equal. Now all I have to do is compute this number. So I'm going to keep the first part of it, which is my number z to the third, and then go ahead with the computation. Now what is 8 raised to the third power? This is my number 8 multiplied by itself 3 times. And when you do that, the answer is 512. Now, as far as the rest of it, I multiply 3 by 15, so I get 45 degrees. And then same thing for sine, which is going to be also sine of 45 degrees. And then you're done. So that's your solution. Now, I already typed in the last part for the partial fraction decomposition. That's going to be recording number 3, but most of the work is typed in, so all I have to do is go over. But this file now, as it is, will be saved and then posted in Brightspace. So let's go back to our folder. It is the video recording notes. And then I will save it as a PDF file as well, and then post it in Brightspace, in addition to the links. There you go. Let me stop recording.